It's a great pleasure to see you all here in Montreal. It's very exciting for JC and I and Jacob, who is with us on Zoom today. We'll be here in person on Wednesday. We started talking about planning this workshop in 2018, I think. In 2018, we had the seed to start preparing for this workshop. So it's really incredible for us that it's finally taking place. We have a few brief announcements we want to mention. So the first one is about masks. As of this Saturday, Montreal has lifted its mask mandate. So masks are only mandatory on public transportation and in health facilities. The CRM still encourages participants to wear masks and take caution, but nothing is mandatory. As you notice, I'm holding this microphone right here. There are microphones scattered throughout the audience. So whenever you want to ask a question throughout the lectures, please request a microphone and we'll pass it over. Lightning talks. So we talked about this throughout our emails. Please come see me if you want to sign up to give a lightning talk. Please start coming to see me starting the first coffee break. JC and I will prepare the schedule this afternoon. What else? Lounges. So we have a beautiful lounge, which is here to our right, which will be open throughout the entire duration of the workshop. All the coffee breaks will take place in there. There's also a microwave. It's a great place to meet and discuss math. There's lots of blackboards. On the floors, there's also a lounge that has a refrigerator and a microwave. Anyone wants to bring their lunch and heat it up. Do you want to say something about the coffee breaks?
So coffee breaks will happen at the end of every day, except Wednesday when the afternoon is free.
And Friday.
And Friday, because there is a reception, I think, at the end of the day.
So we have the coffee break every morning, and we added an additional coffy break at the end of every day.
Good morning coffee. Sorry about that.
The very important morning coffee break. And finally, if there's any questions about where to get lunch or anything like that, please refer to the information sheet, which I sent out. And if you didn't get the information sheet, please come find me and I'll send it your way.
So I think you may have seen that the schedule is relatively light. Like we thought it would be good to have a lot of space for questions, etc. So really encourage you to ask questions during talks, after talks, during breaks. Like it's been 3 years for me that I attended the conference, so we're here all together to have exchanges and participate, etc. So really don't feel any barrier to expressing what you think, etc.
I think we're ready to get started.
All right, perfect. So it's my great pleasure to introduce Scott Armstrong from New York University and the Quantitative. And he will speak about elliptic homogenization from qualitative to quantitative.
Thank you. So thanks to the organizers for inviting me. It's also my first time giving a talk in 3 years, so I don't know if I still know how to do it. I wrote slides for myself just to keep myself on pace. So I'm going to give a course on homogenization, which is very basic. So if you're a homogenization expert, you may be bored, especially at the beginning. And to anyone who is unfamiliar with homogenization, please interrupt, ask questions. Especially the beginning is for you. I'm going to try to move at a reasonable pace, but still give some details, kind of strike a balance between going super slow and going over every detail and going too fast. Okay, but if I do go too fast, please stop me. I'm going to talk about elliptic homogenization, which is a topic I like very much. So I'm going to be mostly focused on, so what exactly am I? So I'm going to talk about elliptic PDEs, that is PDEs in divergence form like this. There's a whole theory of elliptic equations that's not in divergence form, but that's for a different time. So I'm going to talk about divergence form elliptic PDEs. So in coordinates, this is written like this. Okay, so we have this thing in here is the flux, this matrix times the gradient of the unknown, and we take its divergence. And the idea is that the matrix A of x is going to vary on a small scale. And we're going to study the solutions on a very big scale. So in this scaling here, you can imagine that this matrix A varies on scale 1. Maybe it's in the beginning, I'll have it be periodic. In any case, it has some oscillations, and the typical wavelength is of order 1. And this domain U is very, very large. So imagine a ball of radius 10 to the 100 or something like that. So we want to understand what the solutions look like. So yeah, so I've written that. I should zoom this out a little bit. Okay, so in the beginning, like I said, we're going to assume that our matrix is some measurable map from all of space into the set of D by D matrices, which may not be symmetric, but you can assume that you can take them to be symmetric if you want. The two conditions I'll have in the beginning is that we have, first, the matrix is uniformly elliptic. if the matrix would be symmetric, this would be equivalent to the statement that the eigenvalues of the matrix are between this little lambda in light purple and this big lambda in gray. But if the matrices are not symmetric, then you should write the uniform ellipticity condition like this, which is a lower bound on the quadratic form of the matrix, as well as a lower bound on the quadratic form of the inverse of the matrix. Usually people write the uniform ellipticity condition. So this is like an upper bound on the matrix, is the lower bound on the inverse. Usually people like to write this as just A of x times E is less than lambda times E. And this is equivalent, but it changes the lambda. Okay, so if you write, so I think that this one implies this one, but for a constant on the bottom here, instead of lambda, you'd have to have big lambda squared over little lambda. So it changes the ellipticity constant. And so most people don't pay attention to that, but actually I think it's important to write the condition like this for reasons that maybe I'll explain later. In particular, if you do elliptic regularity, starting with just basic energy estimates, and you use this condition, then all of your estimates are the same in the symmetric case. But if you use the other condition, you have strange constants that appear strange if you have a non-symmetric part of the matrix. Anyway, this is my ellipticity condition. This condition we'll find will be closed under homogenization, which is nice. Okay, my second condition is that the matrix be periodic. So if I do a translation by an integer on ZD in integer lattice point, then I have the same thing. So this is a very simple situation. The periodicity means you can basically analyze everything. That unless you're asking some very fine questions, that most of the questions are pretty easy, at least for this equation. If you change the equation up a bit, maybe things can get a little more complicated. But in terms of how the environment is, the disorder of the coefficient field, this is about as simple as you can get. And so it's important to understand this case because it's the simplest. If we can't understand the simple case, then we shouldn't just move on and add complexity. So I'll try to explain how periodic homogenization works. And then later, maybe in the second hour, I'll explain how you can do some random stuff and what make the coefficient field a random field, and how that would change the theory and what the difficulties would be. Questions so far? Usually when people talk about homogenization, they introduce this little parameter epsilon, which doesn't really play any role except to kind of help you understand the scalings of various things. So sometimes we call it the theatrical scaling because it's completely unnecessary, but everyone does it. So if you're the only weirdo who doesn't do that, then everyone's confused. So I'll go ahead and adapt this for now. If you try to state all your theorems with epsilon equal to 1 and the big scale with 1 over epsilon instead of 1, then it's confusing for everyone in the beginning. But this parameter epsilon is just the ratio of the microscopic scale to the macroscopic scale. And we usually take the macroscopic scale to be 1, or at least we do in the scaling. In which case you should write your divergence form operator like this, because after you rescale the problem, you shrink the lattice down to epsilon ZD. And so you write your coefficient field like that. Like I said, this is theatrical because it's not that scaling it's just a change of units. But it helps your intuition because when you're trying to understand, what's the leading order term and so on, it's sometimes better to write things in this scale. But that's sort of the only. So now I'm going to try to do what one normally does in homogenization theory and say, I'm going to look for a large family of solutions. So I can at least have some solutions that I understand before I try to understand all the solutions. And so I want to first kind of give a physicsy argument for how this should work. Okay, and this is sort of what one usually does in an introduction to homogenization course. And when you think about how this operator should behave, okay, so what is this elliptic matrix here? This elliptic matrix tells you how much flux you get for a given gradient. You know that this operator, for example, comes up in electrostatics, and you can interpret the matrix as being the conductivity of the material. So you have a disordered material, and this is telling you the conductivity of the material at that point. It may not be isotropic, so it may conduct in one direction more than the others, and so on. That would be if this matrix was symmetric. But anyway, you can imagine what that would do to the solutions. The solutions would have little wiggles because the coefficient field has little wiggles. And the electric potential, I guess, would be the solution in this analogy, and the electric potential would inherit some sort of fluctuations on the scale of the coefficients. But if you think about it for a while, if you study this operator in a domain of order 1, so the A epsilon is oscillating on scale epsilon, you should convince yourself that the only sort of wavelengths around are the wavelengths of order 1 and the wavelengths of order epsilon. You shouldn't have any wavelengths of order square root epsilon, at least unless you add, at least that should be your naive expectation. If you pose this in a bounded domain, there could be a boundary layer that has a strange thickness or something like that. But just thinking very naively and vaguely, in the interior, there should be only wavelengths of order 1 and order epsilon. And if you think about it more, you realize that the fast wavelength, or sorry, the fast oscillations, the small wavelengths, should kind of ride on top of a wave of a slow moving function. So there should be sort of a macroscopic function which is moving slowly. Maybe I'll draw a picture. I think there's a picture on my slide, but oh no, but I can't because there's no camera for those watching at home. Oh, there is a camera. That's as well as we can solve problems in life, right?
Yeah,
that's the best that we can hope for.
It's not a math problem. So
Yeah.
Sort of.
All right, so this is like a sine, but this is my macroscopic function, and the macroscopic wiggle should be on top like this. And I think I've had this same picture drawn on my next slide. But if you zoom in here, you see that you kind of have a very straight, almost flat thing, because at leading order, it's linear. And we imagine that if the only wavelengths are on the big scale, that means it's smooth, and that then these wiggles should look like that. So it's a sort of periodic wiggles on top of a straight line or an affine function. Okay, so this, so that's at leading order. If you allow for this not to be completely affine, but at next order it's going to have a slight curvature, then there should also be some wiggles for the second derivative, because the second derivative will also cause some wiggles. And if you think about what all this should mean mathematically, you end up writing down in ansatz like this, like a guess for what the solution should look like. Okay. So there's a lot of information in this ansatz, but the basic idea is that your solution, U epsilon, say that U epsilon is going to be the solution of this thing, but that's what I had intended. It's going to be this sort of macroscopic function plus a bunch of wiggles. And the wiggles are kind of linear in the derivatives of the macroscopic. And these things here are the wiggles, and the wiggles are on order epsilon. Okay. So now what I'm going to do is, now that we've admitted this ansatz, I'm going to take this thing, I'm going to plug it into the operator, and I'm going to try to see if I can design, choose these things, and these wiggly guys, and this macroscopic guy, so that it works out. And I'm going to see what they have to be. Okay, so we can do this. So I should say I'm writing these things. Sorry, I'm using multi-index notation. So this alpha is a multi-index. So like, for example, the alpha could be, differentiate 3 times in the x1 direction and 2 times in the x4 direction, or something like that.
What's m in that ansatz?
I'm just summing over all non-negative integers m. I could have just summed over all multi-indices. I don't know why I wrote 2 sums. Okay, so I rewrote it here at the top. So what I intend to do now is I intend to plug this into the PDE and to try to find equations for the macroscopic. So now it's called capital U, apparently. I'm going to try to find equations for the capital U and for these phi alpha. And so I'm really going to compute this for you. So here we go. So we're going to compute the gradient of this. We're going to put a nabla here. When we compute the gradient, a nabla goes here. That's fine. That's this one. And now I have to put nabla in here. And you see by the product rule, I should have 2 terms, right? I should have a nabla hitting this U, which is, I guess, here. I should have a nabla hitting the phi alpha, but that makes an additional 1 over epsilon pop out, because there's an x over epsilon. So I have 2 terms. I have this term, and I have this term. I guess I forgot to say I should have emphasized in my ansatz back here, which I didn't write. That's because I didn't write it back here. That these things I was gonna, I should have said, that's why I wrote the m. There should be epsilon to the m here. So the wiggles that are corresponding to the higher derivative should kind of be next order in my expansion in epsilon. Let's just admit that we believe that. Okay, so that's why there's an epsilon to the m here. So now that's why I have an epsilon m minus 1 here, is because when I differentiated, I had a 1 over epsilon pop out. Okay, so now I'm going to, so this there should be a bracket here because I'm summing over the whole thing. And I'm going to collect the terms now. Let's see, how am I going to organize this? I think I'm going to reindex things here. It looks like what I did is I reindexed things so that this term is now going to be written here. And this term is here, but I reindex this term so that I subtract I subtract one order off this multi-index instead of having one more here. Okay, so I collected terms, I just shifted the sum. Okay, and here I'm writing it in coordinates so that I can, and that's why there's an EI here. Okay, so it's hard to write this in all this detail without some sort of tensor notation or something. And so this is the simplest that I can do it. So now that but the point is you want to organize this so that powers of epsilon and derivatives of the macroscopic function are here, and all of the fast stuff is here. So it's like we factored it to fast and slow. And I guess I wrote it in one more line. Now I write it in one more line. I'm going to go ahead and put this guy as part of the sum, but you're supposed to understand that phi of any negative index is 0, and phi of 0 is 1. So that the derivative is 0. So wait, no, did I say this right? No, I said it backwards. Sorry. Let me write what it was. Phi. Sorry. So am I confused? Yes. Phi of 0 is 1, and phi of any negative index is 0. And so you can put this one in there because this one this one will be equal to 1, and it'll pick up when alpha is 0. When alpha is xi, this one will be 0 and it'll pick up 1. And so I can put this one in there. So anyway, sorry, I'm a little confused here. I end up with this expression. So I have this sum.
Are you sure phi 0 is not the identity?
Yeah, I mean, for any alpha that's of order 0, it's 1. And then for any negative index, it's 0. I think it makes sense. Is it confusing? Yeah, phi of 0 should be 1, and there's only one phi 0. So you're used to like doing this more explicitly, and I'm doing it kind of in some sense abstractly. It can be confusing. So anyway, now what I'm going to do is I'm going to multiply by the. So I just wrote up here what I had done in the previous slide. I'm going to multiply by this matrix, the thing I had done before, the thing that's here. I'm going to take this thing and multiply by the matrix and compute the divergence of that and to get my operator. Okay, so I have a mess. Now the way I'm going to organize it is I'm going to think of this derivative falling on my entire flux here, and I'm going to factor the product rule or whatever so that I separate when it falls on a fast variable and when it falls on a slow variable. So anytime there's x over epsilon, I'm going to kind of do that together. Okay, and when
sorry, I think I'm still confused about the formula. So when you set n equals 0, don't you have the 1 over epsilon in front, which is bizarre?
Maybe I forgot to subtract 1 from m. Yes, it should be written like m equals 0. It should be this, I think. No, m minus 1 is correct. Yeah. When m is 0, all terms are 0. Yeah. Yeah, this made more sense when I was doing it yesterday. It's hard. If you. Okay, so each time you do this calculation, it's an adventure. Okay, so anyway, you write down this entire thing, and basically it's this expression here, which I should have copy pasted the one I had on the previous slide with where this was in here. But anyway, you multiply by this matrix, and when you take the divergence, you again, separately do all the terms of order x over epsilon. So like this, as being separate from, I guess, the slow guy here. So in the first line, I'm going to do all the terms that when the derivative hits x over epsilon, and I'm going to just use the variable y equals x over epsilon when I do it, and then evaluate at x over epsilon. And when you do that, a 1 over epsilon pops out. Okay.
So just to make sure I really insist on the confusion, just to display that directions like this. So then the sum starts at 2 in this expression, in the second one. No?
Yes, in that one, the sum starts at 2 because I forgot to delete this. So let me just delete that term then, Q. So I should have, so now it's correct. Okay, good. I just forgot to delete that term. Thank you. This is the kind of audience participation I was hoping for. So.
Trying to show that even
Thank you.
knowing is okay,
Yes.
you know.
Jean-Christophe can still do homogenization calculations. Okay, so we're going to let the derivatives fall on these x over epsilons. We're going to call that variable y and just put y's here so that it's separate from this x. And it's the derivative of all this stuff, you know, all this fast variable stuff. And we're going to evaluate at this point. And there's going to be a 1 over epsilon pop out. And then the other time it's just going to hit the fast guy. So I get this expression, and now I'm going to try to do something with that. It's actually not so bad, believe it or not. So what you get is when the derivative, so you group the derivative like this. You have this derivative, which where does that parentheses close? Well, I think this parentheses closes. This is hitting these two terms. So this parentheses closes here. Okay. So now we have this expression. And again, I guess the sum, now that the sum should start again at 1, right? Is that what I'm supposed to write? So I think that starts at 1. Yeah, anyway, the 0 term is 0. So you get this, I think even for the m equals 2 term at 0. Yeah, for the m equals 2 term at 0. So anyway, you get this, this expression. So what's going to happen here is that you have this derivative is going to be 1 more than this one. And so I'm going to have to reindex the sum again to make these guys match. Because there's a 1 over epsilon here, when I reindex, I'll actually get the same power of epsilon on each term again. And it's just going to shift this index around. And that's why this index has alpha minus EI minus EJ. This has alpha minus EI. So there's a bunch of terms here. Okay. But this is what the thing looks like. And here we've sorted it nicely so that here it's all macroscopic stuff. And in this bracket, we have microscopic stuff. And now what I want to do is I want to choose my little objects here, these things which are called correctors, by the way. These things are called correctors. I want to choose them so that the stuff in brackets is constant, that is macroscopic. It's constant in the variable y or whatever. Like all the stuff is there. So I want the stuff in brackets to be constant. And the way that periodic function can be constant is it can be equal to its mean. So we're just going to assume that the stuff in brackets is equal to its mean, and we're going to call that mean a bar alpha. So a bar alpha is the bracket of all this stuff. The bracket is what I mean by averaging over the torus. You just integrate over the torus. Okay, and this gives you an equation then for the stuff in the brackets, because if the stuff in the brackets has to be equal to its mean, then we can make an equation. And what we see when we look at this is you see here I have divergence A grad phi alpha. That's like the elliptic operator on phi alpha. And all this other stuff has lower order indices on phi's, which suggests that we should solve this inductively in the multi-index alpha. So I'll write all of this stuff together with the mean on the other side here. This is my right-hand side. And I would like to solve this equation. So I have phi alpha, and I have here the flux of the previous corrector. Sort of. I mean, I have a flux, but then I sum over J. Anyway, so now I'm just looking for a periodic function, yeah, in the variable y if you want. And I want all these guys to be constant. Yeah, I would like just this to not depend on any variable, just to be constant. It's going to be this, it's going to be that number exactly. And so this is just going to contract against that. So I have an equation set in the torus, divergence A grad U phi, phi alpha, or minus divergence A grad phi alpha, equals a bunch of stuff that's mean 0. And you can solve an elliptic equation when in divergence form when the right-hand side has mean 0 by the Fredholm alternative, or whatever. So the condition of being mean 0 exactly allows me to solve it. So we can just go ahead and define the phi alphas recursively.
There you have an infinite sum. So is it clear that this infinite sum is going to be convergent at some point, or?
Good question. Is that infinite sum convergent? No. So this is not in general, but just bear with me for a second. So if you would be a polynomial, then for example, yes. Okay. So if you would be a polynomial, capital U, I mean, then I could find a solution of. Then if capital U would be a polynomial, then this thing would be a polynomial, especially if this is a constant. So I'd have this equals some polynomial. And that would give me a large family of solutions, which is a good thing to do. Okay, and I'll talk more about what you do if you don't have a poem. Anyway, but this tells me what my correctors should be. So I can solve this recursively, and that defines the correctors and it defines the homogenized tensors.
Sorry,
Yes.
so your gradients is in the y variable in your yellow here?
Yeah, yes.
X is fixed?
Well, there's no x in there anymore, actually. There's no x at all, because all the x's are, there's no x here in any of this. So if you look at the previous slide, this stuff had only, it's this, right? It's basically coming from there. Well, okay, so it has a bit, I also factored a bit. So, okay, I combined them, but everything I factored out had x over epsilons at the end of the day. So I can then ask that, yeah, so this should be evaluated at y equals x over epsilon if you want, but I want it to be constant. Yeah, so I want it to actually just equal a constant. Okay, so anyway, that gives me my equations. Oops. This gives me my equations, and I can solve them recursively, and I have all the correctors in periodic homogenization. When the multi-index is equal to 1, then you get the usual first order correctors in homogenization. Yes.
What was the intuition for like why we want the sum of the brackets to be constant again?
Because, okay, yeah, so why do we want it to be constant? We want it to be constant because I would like this actually to be 0 and define a solution. But instead of trying to make it 0 right now, because to make it 0, I probably have to make a good choice of the capital U. So as like just as a first point of business, I want to make it be macroscopic. I want to get the wiggles out. So I want like a thing I can plug into the operator so that the right-hand side has no small wiggles. Okay. And then now that it has no small wiggles, maybe what's left is an equation. Maybe you could call it the homogenized equation that you could then solve and get and then make the thing be. Okay, so now what happens then? Now, if this thing equals this, then that means the stuff in brackets is actually just a bar alpha, and I can plug it in and simplify this expression. So let me go ahead and do that. This thing here in orange becomes a bar alpha, and so I get that this thing equals this thing. So I have this weird. Now, when alpha, so I guess when alpha is 2, this should be the usual homogenized matrix in elliptic homogenization is when alpha is 2, you get this. And people, when they do this, they usually stop at alpha equals, they stop the sum after alpha equals 2. But if you keep going, you get that this thing that we plugged in is an exact solution of this, as long as you can, like we said, make sense of that. Okay, and I should call this now. Okay, now, but now I have to change to red. Anyway, so this thing, this infinite sum, is really the homogenized operator. So when people cut this off at m equals 2 and say, oh, because when m is 3, there's already an epsilon in front. When m is 4, there's an epsilon squared. So usually people cut the sum off at m equals 2 and announce that one term, which is just divergence a bar grad phi, is the full homogenized operator. And that's sort of a lie. I mean, this really is, the thing really does have all these terms. But you can also, if here in my ansatz, I was assuming that I had an infinite sum. You can cut the ansatz at some level and you'll get an appropriately truncated version of this a epsilon, and you can work with that. So you're allowed to truncate. We don't have to be exact. We can make errors because we have a small parameter that we're going to send to 0 at some point. Okay, so if you're willing to live with errors of some power of epsilon, which maybe you are, then you can truncate this and you can say that the homogenized equation is only the first term, which is what most normal people do. Okay, so here's the summary. Suppose that you had a capital U that satisfied weird script A epsilon U equals F. Then you would define little u epsilon to be this sum. That sum somehow makes sense or is convergent. Then this u epsilon would be an exact solution of this. And so that sort of tells you how to fix all the wiggles out of this operator and make it into a different thing which has no more wiggles. Okay, and that's essentially periodic homogenization.
And your phi m you found before, right? The phi m?
Yeah, the phi m we solved in recursively. So the phi m is the phi alpha written in tensor notation. So now I'm switching to tensor notation because it looks slicker. But here I mean, sum over all the alphas. Here there should be a sum over alpha equal to m, and these should be alphas. But I'm just defining this thing to be a tensor of order m, and then this is valued in tensors of order m, and this colon does a contraction. So I can write it more slickly like that. So this is it. This is basically all you need to know about periodic homogenization. But wait,
Scott,
this was still a physics proof. Yes.
do you want to say something about the f function, which didn't appear?
It can be whatever you want.
And what spaces need to?
Whatever you want. I mean, like if you can solve this, if you can make sense of this, then by defining this, if this sum converges, this will be an exact solution of that. F can be an h minus 1 or whatever.
And earlier you had setting f equal to 0. I think.
If you were able to solve this equals 0, then this would be a solution of 0 as a special case. And that would be really good because then you have found the solutions. So it suggests that in order to solve, to understand this operator, we should understand this first. Now, and then just attach wiggles to it in a predictable way, and we've understood. Okay. Yeah, so now there's some more talking points here. So like I was saying, usually people write, so I can write it like this, where the a bar with no subscript is the special one when m is 2. And all of this stuff is some weirdo higher order homogenized tensors, which I insist are really there and are really in the problem. And they're not actually that weird. But this is the one that people usually claim is the homogenized operator. Okay. Now, this is where I answer your question from earlier that you anticipated. In practice, we don't actually invert this infinite order operator, which is after all kind of scary because maybe this part is elliptic, which I'll explain in a second. This a bar is actually going to have the same sort of eigenvalue bounds or whatever as the a of x did. But this stuff is higher order, and usually higher order derivatives are bad in an equation, right? Because they break, the higher order derivatives matter more than the lower order derivatives. But actually here it's the opposite. The lower order derivatives matter more, and this can be treated as a perturbation. I mean, a way to think about this is the way that you solve the equation for the a epsilon is you first solve it for this operator. You find the solution. You plug the solution into this mess. Now that's an error. You invert the elliptic part on the error again so that you knock out the error. You plug what you just got into this again, and you make another error, and you iterate. And you hope that the epsilons being here are going to fight against the fact that you have more and more and more derivatives here. So if you have a very like analytic or something right-hand side, then you can do this inversion. In fact, you can do the inversion on a polynomial. So if you want to solve a epsilon p equals q, where q is a polynomial, you can find a p by doing this, because it reduces the order of the polynomial each time that you invert that part. This part is essentially Laplacian, right? Because the A is a constant matrix, and so it's essentially up to a change of coordinates, it's Laplacian. Okay, any questions? Yes.
So does it have to be polynomial?
To solve that, it needs to be. Okay, so what exactly do you need to solve that?
I mean, can I just assume it's a C infinity function with compact support?
No. You can't do anything like that. So you would need it to be. So if you really wanted to, in the whole space, invert this, what would you need to know about Q? You would need that Q is not only analytic with an estimate, but you would need that the Q, that its derivatives don't even grow like a factorial, like they grow exponentially. So you would need like the kth derivative of Q. So you almost need a trig polynomial or something, like a very regular function. Like I could invert it if it was a slow, like a trig, like sine x or something. It doesn't matter in practice because what you really want to do is not invert it. You want to approximately invert it, because look at this. Say that you're trying to solve this for a particular f that you like. Suppose I manage to solve this for an f which is close to your f. You might live with that because my thing would be an approximate solution. And this is an elliptic operator. So if you have an approximate solution, you can know that your solutions are close. And so that would give you some closeness. And so that's why I say here is in practice, we approximately solve the equations. Indeed, the whole of homogenization theory, like most people don't even write this thing down. The whole of homogenization theory is to just lop off the whole thing from the beginning and do the whole theory, making errors of order epsilon everywhere. Okay.
Okay. So just to confirm, if I assume f is compact supported and C infinity, And then,
Oh, certainly you can't solve it if it's compactly supported.
okay.
Because any compactly supported function will have derivatives growing too fast to invert it. But you can approximately invert it, and in order to know the error in the inversion, I would need you to report to me on all the growth of all the derivatives. Okay, and this really happens in homogenization theory, right? If you want to get error estimates or whatever for your problem, you need to tell me information about the smoothness of the data, otherwise I can't. Okay, and so that's what's going on here. If you have very smooth data, you can. I mean, this is essentially saying if you have very smooth data, then you can exactly solve the problem. Like you can almost write a formula. Okay, so now we come to what people in homogenization theory, if you read any homogenization textbook written in the 80s, particularly by the French school, you'll hear them speak about the problem of justification. So I find this funny to read now. So anyway, they talk about the problem of justification. So what they usually do is they do this exact derivation that we did. We have this two-scale ansatz. They may stop the ansatz at the term m equals 2, but they do that. And they say, oh, this tells us what the corrector equation is. And then they throw the ansatz into the garbage, and they justify homogenization with by other means. And those means are usually indirect and a bit, somehow elegant, but they are not consistent with the ansatz. And so it's a bit funny, and this is sort of up to your personal style. But they do speak about the problem of justification. Now we have to mathematically rigorously justify the ansatz. And so there's got to be like a backhanded way to do it. It turns out though that you can just directly confirm the ansatz. So that's what I'm going to explain. So these methods, at least, and I should say at least for this equation. I mean, for this equation, you don't need any of these methods, but these are the kinds of names they have. And so I'm going to get, the Russians actually had a method that they didn't have a name, or maybe they called it something like the method of first approximation, or they gave it some name. So the Russians had a method, which is basically so all these methods are very abstract in a way. It's like you prove some abstract statement of, you invent some notion of convergence, which has two scales, and then you prove a compactness theorem about it. You prove like several theorems, and then you show that it implies homogenization is true, or something like this, using the corrector equation in some important line. However, the Russians had a method which is like just do what the ansatz said and just write and record the error. So I'm going to show you how you can actually justify the ansatz. So here's the proof that I would endorse is you cut the ansatz off after the first term. If you just want to prove homogenization, like with error little o of 1. So given some capital U, which we'll determine, we're going to take U and we're going to attach the first order correctors. Okay, there's just one epsilon in front. So we're making little wiggles like this to our macroscopic function U. And here's the big idea. We're going to take this thing, we're going to plug it into the equation just like we did before when we were doing the ansatz. Our proof should be faithful to the ansatz because that's actually what's really happening. And then we should, because we're cutting the sum off, we're going to make some errors. Because really, if you look at the thing we did before, we had a kind of cascading sum. I mean, what's it called? Where you have a sum where all the terms are canceling with the next terms in the summation, and we're sort of getting rid of the terms at order 2, and so we should expect an error that's kind of order epsilon. That's what we're going to do. We're just going to plug this in and compute the error, and we're going to assume that the capital U is a solution only of the the sort of leading order part of the big homogenized guy. Okay, so what we're going to do is we're going to plug this in. We're going to see how much error it makes. And then if it makes an error that's small, like we're going to end up with something like this, then we're going to know, because we can invert, because this thing has a bounded inverse, that the distance to the true solution is O of epsilon, which means that we have a formula for the true solution up to O of epsilon. And therefore, since we have since we have this, we can also just delete this part of the sum and make an error of order epsilon. And that tells us that this guy is order epsilon away from the U, the little u epsilon. Okay, that solves the problem. Okay, so let me state now a more precise version. So here's this is a lemma that, like, instead of having the calculation in the proof, it has the calculation in the statement. Okay, so take any bounded domain, take any u, and I'm choosing a lot of regularity that I don't really need, but let's just assume that has two derivatives that are bounded. Define that two-scale expansion thing that I did. Now here's the exact calculation. I won't do it because we already did all the calculations in the ansatz. And I'm going to write it a little bit differently by having some weird functions here. But this operator equals the elliptic part for the u that I plugged in. So in particular, if the little u would be a bar harmonic, this would be 0, plus some order epsilon error, which is in divergence form. This is an identity. You can prove it in like 5 lines. Okay. Now, what is this S epsilon? This is a clever way to like write the fluxes in potential form. So before I had all these matrices A times, I had a bunch of terms, okay? And I'm going to write these terms under a divergence sign, you know, because that's very clever. And that you know, by writing it under a divergence sign, you see that the term is really of order epsilon. Because if I ran the divergence through here, a 1 over epsilon would pop out, and I would have something of order 1. So it's just nice when you write it to write it like this. Okay, so this makes it clear that the distance of w epsilon to some solution is of order epsilon. Okay, yeah. So here's the sort of way of thinking about it, where this error is of order epsilon, and the right way that you measure, you know, what does an equal sign mean for an elliptic equation? It means the equal sign is in the sense of h minus 1. People sometimes say that this is called a weak solution, but it just means that you should always interpret every equal sign in the sense of the space h minus 1. So anyway, these are the flux correctors. So here's the whole calculation. I was intending to go through it, I guess, but maybe I'll skip it because you can see that it's the same sort of calculation that we just already did. It's just that because I've cut the sum, you have these terms that don't end up canceling with the next term in the expansion. And this is the kind of term here. You see, it's like this thing is kind of the flux of the corrector, and this is the A bar, which is kind of the averaged flux. And so this thing is a divergence-free field because the corrector solves the equation, and this is a constant. And because this is a divergence-free mean zero field, I can write it as the divergence of a skew-symmetric matrix, which is kind of Helmholtz. It's whatever. It's writing the divergence. A divergence-free vector field as in potential form, if you want, right? In electrodynamics, this is called the vector potential of the magnetic field or something. Okay, anyway, you do the exact same calculation that we got before, and you're done in that much time. Okay, and so now you have there's supposed to be epsilon here. So now you have written or you have found a solution that's close to the homogenized one. So how do you conclude? Here's the corollary of this. If you have any bounded domain and you have some data here that's in W to infinity, you could, for example, get your U by inverting this homogenized operator with right-hand side equal to F, in which case this would also be F, and then you would have the same problem for U epsilon, but that's kind of redundant, so I'm just going to put it there. So this is, yeah, you have a Dursley problem for your heterogeneous operator. This equals some data, where this is equal to the data on the boundary. What you do then is you take your data here, you define this expansion. Then the true solution, U epsilon, is close to your U like this estimate. And that's what you get out of the previous line. Because the way you actually prove this, which maybe I should stop in 5 minutes, or maybe I can. The way that you actually prove this is you prove that, so these are all weak norms. In other words, I don't know that the U epsilon is close to the U in H1. That's too much to hope for because these wiggles and the gradient of these wiggles are going to be making an error of order 1. But I know that in L2, they're going to be close. And their gradients are going to be, the gradient of U epsilon is going to be converging weakly to the gradient of U. And a way of quantifying weak convergence in L2 is just to use the H-1 norm. That's a strong norm that means weak convergence in L2. So, and you also have weak convergence of the fluxes all in one little package. There's a question. Sorry,
I don't understand what W is doing in this corollary.
Yeah, so you're right. So I don't need W in the statement. I guess I should have edited that out. It's because usually when I state this, I also state it with the estimate that, so I was kind of working to that. These are all weak norms because I'm comparing U epsilon, which has wiggles, to something which has no wiggles. And so it can't possibly converge in a strong norm. But what the statement really should say is that in the strong norm, these guys are close, bounded by the same thing as I wrote down here. Okay, and then, so this is what you prove. You prove this because you're like, hey, look, because of what I said in the last slide, this is actually basically a formula for my solution. And you say that by saying, and then you're going to make an error. So you invert the elliptic operator on the error, and you say that in the gradients in L2 are bounded by this junk. Okay, and that implies this thing, which is what people would usually want to see in a homogenization statement by the triangle inequality, because the W is close to U because I can lop off this part. And so I can kind of replace W epsilon by U in weaker norms.
Can I have a very stupid question, but what's the difference between the L2 difference and the gradient in H-1?
Yeah, so these are the same, and I just write them sometimes to be redundant. Yeah, so those are equivalent. Yeah, thank you. Yeah, so this and this are equivalent, but so what I would really prefer to do is to not write this, but then that would confuse too many people, and so I include this just so it's clear that that U epsilon is close to U, which is what people want to see. So good point. This and this are actually equivalent. They're the same size by the Poincare inequality dualized, and so that's right. Actually, this is even a stronger H-1 norm if you want to know the truth, because it's the H-1 space defined not with respect to zero boundary data, but with respect to mean zero functions. Okay, so now why, I should stop, but just let me say, why is it epsilon 1/2 here and not epsilon? Because everything was of order epsilon before. So what is the source of that error? Is that error really there? The error is not, okay, so the error in this estimate, in this strong norm estimate of U epsilon and W epsilon, there really is a square root of epsilon. And the reason is that when you do this expansion here, you mess up two things. You mess up the right-hand side because it's not going to be an exact solution because I cut off the two-scale expansion after one term, but you also mess up the boundary data. And the boundary data is going to make the boundary data wiggle, and you have to fix the wiggling of the boundary data. And that's actually going to, the boundary layer error that you get, you're going to make a boundary layer. The wiggles are going to kind of damp out as you move away from the boundary. But at the boundary, you have a wiggle. And the wiggle in the gradient is of order 1. So it's sort of making an error in this expression of order 1 at the boundary. And that's going to persist at least a distance of epsilon into the domain. So you're going to have like, I shouldn't write, but you're going to have near the boundary a distance of epsilon. You're going to have an error of order 1. And when you compute the L2 norm of that, you get square root of epsilon, and that's the source of the square root of epsilon error. Okay, the other error that comes from the homogenization error is of order epsilon. Actually, these terms here, these weak norm terms, actually don't see that square root epsilon. They don't see the boundary layer error, in fact. So for when you're estimating these terms, this estimate is not sharp. But when you're estimating these terms, it's sharp. Okay, maybe I'll stop now and I'll this little corollary at the beginning of my second lecture.
Are there any questions or comments on this first lecture?
Back to the corrector equation. Yes, Miss, why the corrector equation has a solution?
Why it has a solution?
Yeah.
Okay, so we're going to solve this inductively. So imagine that we're going to solve all the guys of order alpha equals m at the same time. And we've already solved the equation for all the guys of order m-1 and m-2 and below. So everything on the right-hand side, all the phi's have lesser order, okay? And this guy is just the average of this stuff. So this is also well-defined. Okay. So this right-hand side is a mean zero object in H-1 of the torus, okay? So from basic elliptic theory, you know that if you have a divergence form equation that's uniformly elliptic, and the right-hand side is mean zero, that by being mean zero, it's orthogonal to the first to the eigenfunction with eigenvalue 0, which is the constant. Okay, and so that means by the Fredholm alternative that you can invert this guy exactly on those functions. So it's the condition of being mean zero that allowed me to solve it. If I didn't put this here, then I couldn't solve it. So that's the reason, that's where you see the A bar. right? And it makes sense, right? Because if this here is supposed to kind of average out, then it should average out to its mean, and its mean should be the thing that's multiplying that. The way that you see that is you solve that equation.
Do you have an interior estimate? So you said that the epsilon to the 1/2 is just because of the boundary layer. Is there an interior?
Yeah, so this is all, yeah, so like everything here is super well known in classical. And the boundary, so I'm trying to find it again, sorry. Here, yeah, so if I was being sharp, here, then this should really say epsilon. And the reason is that solve the boundary layer problem separately. And when you solve the boundary layer problem, you can prove that it's true that the error is O of 1 near the boundary, but it's only in the boundary. And then you can say, well, if the you can compute the L2 norm of that. And because you're confined to a boundary layer, you pick up an extra factor of epsilon from the Poincare inequality because the boundary layer is thin. And so you find that when you are looking at these guys that you don't see it. Because you can kind of triangle inequality these guys at the level of U epsilon minus W epsilon. So U epsilon minus W epsilon you can show is of order epsilon. That the leading order contribution to that is actually the error in the homogenization problem. The boundary layer is the leading order contribution to the error in the. So to really do the expansion, so I did kind of the full expansion in the interior. To do the true expansion, if you wanted the Dursley problem, then I would need to introduce more higher order correctors that correct the boundary layers. And then those boundary layer correctors echo off the other higher order correctors and create a gigantic mess. Okay, and now the problem is that we can't actually do that sufficiently well because nobody can still analyze the boundary layer problem properly. Okay, so the boundary layer problem has not been done well enough that we can do that.
I think we have a question from the virtual audience.
Question from the virtual audience.
Yeah. I also want to ask something about boundary layer. So as for the last corollary, if you study the problem in a compact manifold or like torus, there's no boundary. So
yes,
the next order thing should be epsilon rather than epsilon 1/2.
Yes. So I just stated this for the Dursley problem because that's one choice you can make. Any problem you have amounts to, so here's how you solve any homogenization problem, okay? You say, okay, you want to homogenize the Dursley problem or the Neumann problem or the Green's function, the parabolic Green's function, any problem you want, what you do is you say, okay, look at this problem. How do you prove uniqueness for that problem? Okay, well, convergence is quantitative uniqueness. So take your uniqueness proof and put the correctors in there or something, and now that's it. And that should, you quantify your uniqueness and you have your convergence. So I chose the Dursley problem. The Dursley problem, though, kicks up these boundary layer errors because it's not, when you go to the boundary, it's not about homogenization anymore. It's about clamping to the boundary condition. So the problem kind of changes near the boundary. But I could have posed this in the whole space and put in an F on the right-hand side that was C infinity or something. And if I did that, then I would probably have used higher order correctors and I'd have an error like epsilon 1000 or something. I mean, you can get arbitrarily good if you have no boundary layer. So if you have a right-hand side that's very smooth, then the error you should get is the epsilon to the k, where k is the number of is roughly the number of derivatives of the right-hand side that you have.
Another thing about boundaries things, like before you were saying that you want to solve the approximation problem that has epsilon all the time with derivative. So it's like you keep invert elliptic operator. But if the thing if the problem is at a boundary, can you still do that kind of stuff? Like,
yeah, okay. So I think your question is you want to solve the higher order operator, but then the boundary is a problem?
Yes.
Yeah, so in order to do the higher order expansion for the Dursley problem, so I did this higher order expansion where we had more and more and more terms and powers of epsilon. For the boundary layer problem, or for the Dursley problem, the boundary layer makes an error of order epsilon 3/2. You have to do a full expansion of the boundary layer in order to get past epsilon, epsilon 3/2. Like if you want epsilon to the 8, you can use the 8th order interior corrector, but it'll be useless unless you've done at least 7.5 derivatives of the boundary layer guy, and no one knows how to do that.
Okay, thank you.
So that's open. That's the last problem in homogenization in the periodic case that's open. That's actually non-trivial, whereas the rest of this is fairly trivial.
Any other question or comment? or suggestion to solve the last problem of homogenization? No? So if not, then we're going to, well, thanks Scott again.
It's too much.
And then we have a break until